So let's pick up where we left last time. I think I enunciated a couple of theorems that I didn't prove. So we were talking about extensions of R modules. I think I was talking about right R modules, but it could have been left R modules, and the X groups. So what was the construction I did last time? Was by considering an extension of the form M into E into N 0. This is in mod R. And I wanted to construct a class in the first X group of N by M. So what we considered is hums into E from this. So what I did is I looked at this mapping into X1. Oops, no, this is wrong. And N mapping into X1 and M. By looking at a sequence that is the sequence that takes hom N into this thing. So if I look at hom N into this thing, then I look at hom NE, hom NN, X1, NM. And this sequence is exact. And we said, well, we always have this element here, which is the identity of N. And this was constructed by this abstract nonsense of homology theory. But whatever that delta is an element here. And now, if delta is 0, if X1 and M is 0, then this delta is always 0. And if this happens, then there's a lifting here. There's a map from N to E that maps to the identity of N. Because this sequence is exact at this point. Well, so I don't really need this group to be 0. I just need this delta of the identity to be 0. So if this happens, then this sigma exists, and then therefore this guy exists here. Now if I call this map pi, I'm saying that the composition of sigma with pi is the identity of N. So this is a section here. And now we have the following situation. We have M, we have E, we have N. That's one exact sequence. We have M, we have M plus N. We have N. That's another exact sequence. Here I have the identity. Here I have the identity. But now I've gotten a map from N to E, which is this sigma. So in particular, this gives me a map from M plus N to E, which grabs an M here, puts it there, and it just maps it by this inclusion, and grabs an N here, which is the same as this guy here, and just maps it by sigma here. So the map from here to here is given by the inclusion on M and this projection and sigma here. And this is obviously an isomorphism because these two guys are isomorphic. So the upshot of this story is that if delta of the identity of N in the X group in x1 of nm, then the sequence is split. So that's essentially where we left out. So this sequence here is split if delta of the identity is 0. And I want to prove a converse of this. So that's where we left. Now I want to prove a converse. I actually want to say that I have an equivalence class, an isomorphism of equivalence classes of extensions of n by m, where n and m are fixed, and this X group. So theorem, there exists a one-to-one correspondence between isomorphism classes of extensions like star and this X group. And if you give me an extension, then the element of x1 is given by delta of the identity of n. So if you give me this extension star, you map it here to delta of the identity of n. And you claim that map is bijective. So let's construct that delta in a different way. So here we're going to play the following game that, remember, we balanced already the home functor. And we said that we can compute this derived functor of home between, say, here I'm doing n and m, by either taking home of a projective resolution of n into m and taking the homology of that complex, or taking home of an injective resolution of m and taking home from n into that complex and taking the homology of that complex. So here I'm doing something very silly, which is I have this short exact sequence and I took maps from n into this. Let's actually take a projective resolution of n and let's compute this x the way we would do it by taking a projective resolution of n. And we don't really need the full projective resolution, we just only care about x1, so I'm going to take only one projective over n. Let's look at this kernel of this guy, it's whatever it is. Let's call it k. That's a short exact sequence. So this by definition is just the kernel, but I'm taking a projective that lives over n, and I know this exists because the category of right R module has enough projectives. So let's pick any projective. Pick this identity like here. And, well, P is a projective. Let's suppose that I start with an extension. This is the extension I started with. P is projective, and I have a surjection here. This sequence was exact. And I have a map from P to N. Therefore, this lifts. This exists because P is projective. Now, this is the kernel, so this is just the kernel of that map. So this exists. Okay? So now, what I realized is that, well, from the extension, this was my extension, I constructed this morphism here, which is a morphism from k into m. Let's put a name to this morphism, whatever we want it to be. Let's say alpha. And this guy is going to be beta. This beta exists because P is projective. All right? Okay, so now let's look at taking homes from this into M, from this sequence into M. And what is the long exact sequence that I get in homology? Well, it's going to look like hom from P into M that maps into hom from K into M. This is not something fancy. If I have a morphism from P to M, I just compose it with this inclusion and I get a morphism from K to M. But then the next step is X1 from N into M, which is the group that we're interested in. And here I have my beta. And this was delta. So this is delta of beta, which is a class in X1. Okay. So again, from my extension, picking any projective on top of N, I constructed a class in X1 and M. So we also knew that delta was natural. In the sense that if I had two short exact sequences, say A, B, C, and had another one, B prime, C prime, and I have a map of short exact sequences. Then I get a long exact sequence in homology. I guess, yeah, so I'm going to do homology. We have Hn to Hn, B, Hn, C, Hn minus 1, A, Hn minus 1, B. And the same thing for the primes. This map I have because this guy is functorial. Hn, B prime. This guy because this guy is functorial, Hn C prime, because this guy was functorial, Hn minus 1, A prime, Hn minus 1, B prime. So all of these arrows I get, but this one didn't come for free. The fact that this diagram commutes was not for free. This was a construction that the delta functor that we constructed was a natural transformation. So that implies, by using that and using this map of historical sequence, that this delta of beta that I constructed there actually has to be the same as delta of the identity of n, of this hom nn, which is natural. I mean, the fact that we are constructing a class in X1 in this group, just starting from the extension, it's clear that it shouldn't depend on the choice of this projective guy that I chose here. So this delta of beta is the same thing as my class that I'm just going to call it now theta of this extension. I'm going to use E for the extension. This E is not the module, but it's actually the fact that it's an extension of n by m, and it's delta of the identity of n. Now, why did I say beta? Beta is here. I think I know. I think the book uses beta there. It's alpha. The map is from hom km to x1. All right. So we constructed now this class in two different ways. And I'm saying that this class, I'm defining this object by being this guy in x1. I claim that this object depends on the extension, and it doesn't depend neither on the projective nor on any choice. If I pick another extension that is equivalent to E, then I'm going to get the same class in X1. So let's prove that. I just wrote this. So claim theta is so defined, which is this map here, depends only on the isomorphism class here. Already that statement there was shady. I was taking an isomorphism class of extensions. I took one extension E, and I sent it to this delta of the identity of n. I should have said that this does not depend on the isomorphism class. It only depends on the isomorphism class and not on the representative. So let's prove that. And this setup is slightly easier to prove that statement than if I had taken this setup here as a delta of the identity. So let's suppose that we have, so I need a couple of lemmas before. I think we've already used, but in the category of R modules, the following coproducts exist. So fibered coproducts exist. So I can look at this kind of diagrams. Let's call this guy I. Then colimits indexed by that diagram exist. So what does that mean? This means the following. If you give me 3 modules, A and arrows like this, B and C, there exists a colimit, we call that guy X, with maps from C here, from B here, from A here, such that every triangle here commutes. And with the universal property that if I have another X prime with the same things, mapped from C, from B, and of course you need to get it from A just by composition because this diagram commutes. So this arrow here, I don't need to give it to you because this arrow needs to be the same as this. So whenever you have these maps like this, then this here exists and is unique, and this one is actually unique. So that's the universal property of this coproduct. I claim that this guy actually does exist in this category. It's not true for an arbitrary category, but in this category it does exist. And it's constructed, since the category is abelian, we can look at the map from A to B plus C. So what is this map? Well, if I call this map I and this guy J, then this map is just I plus J. And the co-kernel of this map is X. All right, so it's clear that X comes with a map from B and C, because it comes from a map from B plus C to X, by definition. So X comes with this map and this map. These are the two projections. It's clear also that this diagram commutes, because if I grab A, I send it to IA, and then I look at that preimage, or if I look at the image by JA, then since I'm looking at this co-kernel, I'm killing the image of A. So these two guys become equal. So, okay. So probably I want to put a minus there so that they are actually equal and not one minus the other. Okay, so all of these diagrams commute, and I have this X. Now let's suppose that you have another X prime with these maps from C to X prime. So if I have a map from B to X prime and from C to X prime, then I get a map from B plus C to X prime. And I'm saying that this diagram commutes. So if I map from A to C and from A to B, then these two guys get to the same guy in X prime. Then, in particular, this map factors through the quotient by A, which is the same thing as a map from X to this. So this is my X, the quotient of this sum modulo the image of A. Okay, so this colimit exists in that category. Limits also do exist in that category, and we're going to use those limits too. So I think people call that colimit the push out. So this X is called the push out. Of, well, these two maps, I and J. And I think I've used I confuse I and j here. So let's put I and j. Of I and j. Pullbacks also exist. So lemma, in the same category of our modules. Now, this situation is, I'm going to revert arrows. And now these are going to be co-limits. Sorry, these are going to be actual limits. Exist. So this means if you give me 3 modules, A, B, I think I'm going to use the same letters as before, C, A, and B, and you have maps like this, then there exists an X here with maps to B, with maps to C, making this diagram commute, and universal in the sense that if you have any other X prime with maps like this, making this diagram commute, then there is a unique map in this direction. Then there exists and it's unique. Again, this is the same thing. So, well, I'll let you construct this exercise. Construct X. But it's clear what it has to be. You're going to look at B plus C, and then you want to equalize their maps to A. So this guy here is going to be some sub-module of C plus B, which you're going to define it to be the kernel of the map to A, which is given by the sum of these two guys. So here was a co-kernel, and there is going to be a kernel. Okay, so having said so, I'm going to use this now. Let's suppose that we have 2 extensions that are isomorphic. Actually, let's prove this. Okay, let me prove the theorem. Proof of the theorem. So I want to prove that for each extension, I have a class in X1. For each isomorphism class of extensions, I have a class on H1, on X1. And for each class in X1, I want to construct an extension. Okay? So given one extension, I've given you this class in X1. If I choose an isomorphic extension, this class is going to be the same, and I'm going to go back, and I'm going to prove it by going back. These classes are the same. So let epsilon be a class in X1. So I'm going to fix this setup. This setup does not depend on any extension. So let's fix a projective over N, and let's call K the kernel. And I have a class in X1. Okay. So now, since we have this exact sequence, so this sequence is always exact. So I don't want to erase that, but I have this map always here, and I can always pick an element alpha here that maps to my class in X1 here. Why is that? Let's look at the long exact sequence that comes from there. So I could have started at hom k m mapping to x1 k, oh, I'm sorry, nm. And this guy maps to x1 now. P m. But P is projected. So this is 0. Because P is projected. And this sequence is exact at this point now. So that means that this map is surjected. So this meant this map here is surjected. So for every class in X1 that I'm taking it to be epsilon, there exists a homomorphism from K to M here. Let me call it alpha. That maps to that. Okay, so I have my K that maps to P, and I've just constructed a map alpha. So let me call that I, and I just constructed a map alpha to M. This map is constructed as the preimage in hom Km of this epsilon. This alpha depends on epsilon. Now this guy is injective because K to P was by definition a kernel of a morphism. And I claim that this push out of these two maps constructed here as this co-kernel, let's call it X. And this by definition made this diagram being a co-limit. So typically we will denote this way. This square here means this is Cartesian. This means this is the co-limit of this diagram. Okay, first claim, this is exact. So if I have a co-limit and the top arrow here is this is injective. If this guy is injective, then therefore this guy is injective. That's very simple to see. If you had something in the kernel here, then by the way we constructed this X as a co-limit, you're going to pick a lifting here. There exists a lifting here, and there exists a lifting here. This map is always surjective, such that what you get here is going to be in the kernel of this map. And then this I is injective. So this guy is injective there. Moreover, this X, P came with a map to N. And that makes X come with a map to N, which is still surjective. And you get that short exact sequence there. So, okay, I want to describe how do I get a map from X to N. Okay? X was constructed in such a way that this diagram is Cartesian. P comes with a map to N. And, well, to construct a map from X to N, I only need to give you a map from M to N, making this diagram commute. And I'm going to give you the 0 map from M to N. So P comes with a map to N, which is just this composition. M comes with a map to N, which is just 0. And it makes this diagram commute. If I go from K to N, I go to 0 this way, because this is the composition of an exact sequence. If I go from K to M here, and then by the 0 map here, I go to 0 there. Therefore, all of these diagrams commute. And since this guy was universal with that property, this guy exists and is unique. So that way, starting from this guy alpha, I constructed this short exact sequence. So this gave me a map from epsilon. I associated this alpha by just picking any lifting, because this guy was surjective. And I constructed a short exact sequence. But I could have chosen a different alpha. So here I made a choice. I chose one lifting of this epsilon. So what about I choose a different alpha? So let's suppose that I choose alpha prime with the same property, that delta of alpha prime is equal to epsilon in X1. And this construction would lead to a different construction. Now I'm going to start with K by alpha prime is going to go to M I still have this same piece of the sequence, but now the push out of these two maps is going to be a different object, x prime. And again, by the same condition, you're going to get another extension. I claim that this extension is isomorphic to the previous one. So what's the difference? If alpha and alpha prime map to the same delta, then delta of alpha minus alpha prime is equal to 0. So alpha minus alpha prime is in the kernel of this map, and this sequence was exact, therefore they are in the image of this map. That means that there exists some morphism from P to M now, and we call this morphism H. And if I call that guy I, then alpha prime, so there's an H, which is a morphism from P to M, such that alpha prime is equal to alpha plus that correction, which is the map from alpha prime and alpha are both maps from K to M. Now they differ by that map H that I just chose. Okay? Because this is the image, composition by I is the image of this map. Okay. So I have this difference. I have this map H that goes from P to M. All right, so I have this guy, and I want to exploit that to find an isomorphism here. Okay? Remember how we constructed this X, or how we constructed this guy. This guy was a push out of two maps. So now I want to construct, I want to prove that I have a map from P to X that is not my original beta. So this was beta prime. Here from P to X, I have beta. And from K to M, I have alpha prime. And from K to M prime, I have alpha. And to M, I have alpha. Now the push out of these two maps, alpha and beta, is X. And the push out of alpha prime and, well, this guy I here, the same I is this X prime. But to construct a map from here to X prime, what I need to show is that, so to construct this guy here, I only need to make to show that I have a map from P and from M to X that make the diagram with these two arrows commute. And I do have those maps. So I only need to correct this beta prime, because the map from M to X is fixed. This map here is fixed. I only need to correct this beta prime. And I'm going to correct it by just adding H. Or I can correct beta either way. I can either correct alpha here, or I correct beta. So I'm going to do it here with a minus, and I'm just going to subtract this composition of H with this map here that I'm going to call J. So you do J, H. So now, if I take this map here, then I realize that this is the same thing as beta. Therefore, I am finding that these maps from P and from M prime to X satisfy the universal property of the X one. So this guy exists and is unique. And the same thing for this guy. If I just add to this guy JH, then by the universal property of this being a push out, I'm going to get a map this way. And this is an isomorphism. Okay, so I checked that if I choose different alphas, I get the same extension, modulo an isomorphism. And that's it. So in particular, if I grab my epsilon and I construct this extension, E. Then I construct this theta of E, which was given as delta of the identity of N. I get back my epsilon. So that gave me, that shows that this map is surjective onto x1, right? Because I'm going from x1, constructed an extension, and came back to the same guy. So that means that the map from extensions to x1 is surjective. This means that the map from extensions modulo isomorphisms to x1 is surjective. So I need to prove the inverse the other way around. Namely, if I start from an extension, I construct the x1, and then I come back, I get to the same extension that I started with. But then again, that's the same argument as I did now. If you start with an extension like this, you construct this theta as an element on x1, you come back by this projective guy, and by the universal property of the push-out, you're going to get back to the same one. So it's easy to check injectivity of this map as well. And that proves the theorem. All right. So we have this bijection, and what is interesting is that that bijection is naturally, so this is where I ended up last time, that we have this bijection between extensions modulo isomorphisms and x1 classes but this is an abelian group. And this one is an abelian group. So what's interesting is that this guy is not an abelian group. You cannot sum extensions, but you can sum them up to isomorphism. So this is an abelian group as well. And this is an isomorphism of abelian groups. So let's construct the sum here. So extensions form a category, and that category doesn't really have that sum well defined, but modulo isomorphism. And it's the problem is that you take colimits, or you take limits to construct its sum. So let's suppose that you have two extensions, MEN, and you have another extension, ME prime, N prime, N. Now there's no map between them. Any map between them is going to be an isomorphism. So there's no maps between them, but I want to construct a third extension that is going to be the sum of these two guys. Okay? So how are we going to do this? I'm going to use that diagram there. I have my K, P, N. This is completely independent of any kind of extension. But what I checked is that any extension like this comes with these maps. I mean, this is just because of the lifting property of this P being projected. So I have a map from P to E prime, and I have a map from P to E as well. I don't have a map from between these two guys, but I do have a map from P to E prime and to E. So I have that guy there. Okay. So what I will do is I'll look at, I have this map from EM to E and from M to E prime as well. So that's another diagram that I also have. Okay. So what I would look at is going to be E plus E prime and I would want to kill. So this guy has this M. I mean, of course, this is not going to be an extension of M by N. Right. So M maps into here in different ways. It maps from M to E. I have a map from M to E prime, which is this guy, so therefore I get a map to the sum. And then I have this skew diagonal map, which will send, if I call this guy I prime and I guy I, then I'm going to send to IM plus I prime M here. And what I'll do is I'll identify these two. So what I want to do is I want to identify these two inclusions here so that I get N in the corner. So put M here. I want to get an extension here into N. And, well, this I cannot extend here. So the question is, what quotient of these two guys do I get so that this X sits here in the middle? And that's a question for you. So this E, if you think of it as modules, each one of these E wants to look like a sum of N by M, both E and E prime. So I have several copies there of N and M. Right? So if it were trivial, both of them were trivial, I would have 2 copies of M and 2 copies of N here. And I would want to get only 1 copy of those. So what do I quotient by those to get the right thing? So what's the construction of this X as a sum? The sum is too large. I want to get something smaller. I talked about diagrams both. So remember that we also have this diagram. We have a map from E to N, and we have a map from E prime to N. So I could look, for example, that, I don't know, I need another name. X is bad, Y, Z here. So this guy also exists, and I could use that. I'm trying to construct something. So what's the size of this Z, for example? Okay. What would the size of this Z? So this looks like E plus E prime, but I am identifying the projections into N. So the size of this thing would be, if this looks like N plus M and this looks like N plus M, this Z would have 2 copies of M and 1 copy of N. I'm identifying the 2 maps to N. So let's imagine that these both extensions are trivial. Namely, E is M plus N. E prime is N plus M. So I'm looking at something that sits, I'm looking at this C, so let's do this as an example. That here I have M plus N. This projects into N. Let's take here M plus N. This projects into N. What can I put here that makes this diagram commute? and that is universal with that property. Well, I need something that maps to m plus n, that maps to m plus n, that makes this diagram commute, and that has this right universal property. So what I would put here is going to be 2 copies of m, but only 1 copy of n. And the map here is going to send m, m prime, and n to m prime n, and the map here is going to send it to m n, so that they map to n here. But it's clear that I need these 2 copies of m here. Why? Because if you give me any other guy with a map to here and a map to here, they don't need to agree in the copy of to m. They only need to agree once I map to n. On the projection to n, they need to agree. But the map from x to m and the map from x to this m here might be different. And I want to get a map from here to here. So that's why I need these 2 copies of m. Because I would want to map to, if this x map to m here, I want to map to m. And if we map to m prime here, then I want to map to m prime. So that's why I need these 2 copies here of m. All right. So let's so I didn't want to remove that. Let's formalize that in general. I claim that this guy here has 2 copies of m and 1 of n. So let's grab this z, again, let's make it this diagram, which I put e prime here, e. Both of this guy map to n. And let's grab m. And I claim that m comes with maps to z. Why is that? This guy is a colimit. It has a universal property. And m maps to e. And m maps to e prime. And this sequence is exact. Namely, in particular, this composition is 0. And this sequence is exact. In particular, this composition is 0. So I have a map from one object to these 2 guys that coincide on n. By definition, this comes with a map here. Okay, so I constructed one map from m to z. So let's kill that map. So let's look at z modulo the image of n. Let me call this guy x. Well, in this example, if I kill 1 copy of m out of this z, I would get m plus n. So at least this guy has the right size. So I claim that this x still has a copy of m inside, and it maps to n. So I claim that that x actually does the trick. That x does the trick. Okay, so z came with a map to n. Came with 2 maps to n. Either this way or this way, it doesn't matter, but this z came with a map to n. And m here mapped to 0. So the whole copy of m to z, when I compose to n, went to 0. So that means that x still has a map to n. Because the surjection from z to x, which is by definition this quotient, composed with n factors through, this map z to n factors through this quotient. Right? This is just because m maps to 0 here. So x comes with a map to n. Okay, why is the kernel of that isomorphic to m? So we're only left with proving that the kernel of that map is isomorphic to m, or prove that we have a map from m to x. Well, I can give you either map. The thing is as follows. this Z was constructed in an exercise that I didn't do. But I told you what the answer to that exercise was. That we would take these two guys, and inside of this guy, we're going to choose Z to be the kernel of the map that we have from here to N, where we have our E here, or our E prime there, and we map it to, well, if I start with these two extensions, let me call this pi prime and pi. So I'm going to map this to pi of E minus pi prime E prime. Take minus or plus, it doesn't matter. Oh no, I do need minus because I want to equalize this. So the kernel of this map, I'm going to define it to be Z. And that guy comes with a map to N, which is just projected to E, take the first projection, or the second projection, it doesn't matter. Once I look at this kernel of this map, the first projection and the second projections are the same. But the point is that this Z comes with that map to N. Now this is my Z, which is inside of E plus E prime. And M maps here, or maps here, or maps to, I think I call this guy I prime, and this guy I. Then I have three maps here. I have from M to I of M, from M to I prime of M, or the diagonal one, I of M minus I prime of M. Now I've already divided by the diagonal map. So in Z mod M, which is X, this guy became 0. But both IM and I prime of M are maps to this guy. Modulo these two maps are the same, but I still have one map from M to this divided by the image of M, by the anti-diagonal map of M. And I claim that that map factors through here. Why is that? Because, well, both of those maps composed to the map to N are 0. So it has to map to the kernel of this map. So this X comes with a map to M, with a map from M. And now the composition of these two guys is 0. That's clear because the map from M to N, by composing by either projection, was 0. So I get a map from M to X and a map from X to N whose composition is 0. So now the only thing I need to check is that, that this map is an injection. But this is trivial because either of these maps were an injection. So okay, so we've got an extension X. And this, let's review the construction because it's very simple. We've gotten two different extensions. We look at this limit, which is just the direct sum, and you look at the kernel of the diagonal map to N. So that gave us Z. This comes with three different maps from M, either on the first projection, the second projection, or the diagonal one. We divided the diagonal one, and we are left with either of the two projections that are the same map now in this quotient. So that's the map from M to X, and that goes to N. Okay, so that's this abelian. This is sort of like the abelian group structure here, which I haven't given it to you. I given two extensions, I constructed a third one. And I want to prove that this construction is well-defined modulo isomorphism classes. So to do this, so I need to prove that the isomorphism class of this extension which I'm going to define it to be, so I'm defining this side as the sum of the isomorphism classes of the extension of E by the extension of N, is well defined. So I have these two extensions, I define this sum to be the isomorphism class of this extension. I need to check that this is well defined. But I know that I have a map to X1. And I have a map to X1. And to this guy, I have associated a class in x1. So if I prove you that in x1, this coincides with the sum, I'm done, because the sum here is well defined. And these maps are isomorphisms. So I've already proven that there's a bijection between isomorphism classes and x1. An isomorphism class in x1, an isomorphism class in x1. So if I prove that this sum coincides with the sum, the natural sum in x1, then I'm done. So let's prove that. And for that, I need to remember how I constructed the class in x1 associated to an extension. And that was done the following way. I took my kernel from a projective to n. I had this map beta here to E, and I had this map alpha here to M. And the class associated to this extension E was given by delta of alpha. This is in x1. Okay, so the same thing for the E prime guy. Then I'm going to have a map alpha prime into M. And then I have delta of alpha prime. So all I need to show is that the map that I get for the sum extension, so the Bayer sum of the extensions is this extension by x, is given by alpha plus alpha prime. Okay, so I need to check at P maps to N. I have this guy here. Now I have X here. Now I have K, 0. And I wonder, what are these two maps? So how do I construct a map from P to X? So now I'm going to use this. I have a map from P to E prime, which is beta prime. I have a map from P to E, which is beta. And how did I construct this X? This X was a quotient of Z, and Z was given by a co-limit of maps to E, E prime over N. So I look at this. P maps to E prime maps to N. P maps to, by beta to E, maps to N. This diagram commutes. So by the universal property of that Z, this comes with a map to Z. So P comes with a map to Z by the universal property of limits. So P came with a map to Z. So now let's look at what is the copy of M. So, well, it doesn't matter. So P maps to Z, therefore it maps to X, which is a quotient of Z. So this guy surjects into X, therefore I got this map, which is this. So this I'm going to call whatever, beta prime. No, beta prime is already taken, beta bar. Okay, but now I need to understand what is this map from K to M. I claim that this map, therefore, is given by alpha plus alpha prime. So let's check that. Because since this one was constructed by a universal property, I only need to check that this map actually does this diagram become Cartesian, makes this diagram become Cartesian. Actually, this was Cartesian the other way around. So I claim that this guy makes this diagram become Cartesian. And that's easy to see. Well, this map from P here came from this map to Z. And this map was given to the sum of these two guys. You can send from E to one copy here, and this Z was given as a sum. So the map from P to Z is the sum on each of the maps to E and E prime on each component, on each factor. So this map here is the sum of the two maps from P to E and E prime. Therefore, this map that was given as the kernel of that is the sum of the two maps from K to M in both cases. So we have this diagram. And now, to this diagram, we need to compute what is the associated class in X1. But then the associated class in X1 is just delta of alpha plus alpha prime. But delta is a functor in abelian categories. So this is the same thing as delta alpha plus delta alpha prime in X1. That's it. This is the class that associated to this extension, and this is the sum of the classes associated to each one of the extensions C and E prime. So therefore, the sum is well-defined modulo isomorphism classes. Okay, so it took much longer than what I wanted, but that proves this theorem. I should probably stop here, but I'm going to cover a couple of things that we didn't cover in the previous lectures, because I want to move to a different topic, and I want to do two things that I mentioned and I never proved. I think I didn't prove. I haven't looked at the videos either. So let me tell you tell me if I already proved this. But there are two things that I want to do, and I've never proved, I think. So first of all, a characterization of projectives and injectives that is very useful. So an object in the category I is injective if whenever we have an injection like this, a map like this, then this guy exists. So this is the fact that I have a map hom from A into I have a map hom from B into I. And whenever I have an injection from A into B, if you give me a map from B to I, you compose with this injection I, and you get a map from A to I. So you always have this map here, which is the composition by I. Now, I is injective if and only if this is surjective. So this we've already done, if and only if this is surjective. But let's extend this. Let's look at this, and let's take the co-kernel of this map, which we can always do. I think C is a bad idea. Let's call it C. Okay, it's a bad idea for co-kernel. So now, let's look at the long exact sequence that we have on X homologies. So hom into I is contravariant. It's contravariant. So what I get is, I'm going to get a long exact sequence here that goes as follows. So I'm going to have hom. I'm going to have hom. Yeah, let's do it like this. Hom bi to hom ai to hom x1 ki ci. And it continues. Now, if I is injective, then of course all the x's, xn, anything, let's say b, c, ci is equal to 0 for every n bigger or equal than 1. That's clear because I is injective is the same thing as I being projective in the opposite category. That was the definition. Just turn it around arrows. And x n, it was a derived functor. So this would, so whenever you have a projective, all the positive homologies are 0, vanish. In particular, x1 ci is 0 for every c. And this is also for every c. For every c. So this implies this. On the other hand, if x1 is 0, this sequence is always exact at this point. So if this guy is 0, then this is surjective. And the only thing I used is that this was an injection to get this short exact sequence. So if x1 is 0, then that guy is surjective. This implies that this guy is injective. And of course, this implies this. So an object is injective if and only if x1 into that object is 0. So you don't need all the vanishing of all the higher ones. Exactly the same thing for projectives. What was the definition of being projective? Here is, you have B and a projection. You have B and a surjection like this, then I'm saying that this exists here. So the fact that this exists here, if I call this guy pi, again, it's the same thing as hom, but now it's of a covariant functor, hom PB into hom PA into hom PB, that this is surjective. Now, what is this map? If you give me a map from P to A, you compose with pi. And this is surjective if and only if P is projective. So this is surjective if and only if P is projective. Okay, so now again, same trick. Just take the kernel of that surjection. So we're using that this guy is a surjection to make this into a short exact sequence, and not an arbitrary longer sequence. So now this is the kernel of that guy. And let's look at what happens in homology. You get a map from hom PA to hom PB. Now the functor is covariant, so this goes to x1. To hom x1 pk. Same argument, P projective implies that xn pk is 0 for every k and every n bigger or equal than 1. This in particular implies that x1 pk is equal to 0 for every k. But now if x1 pk is 0, then this is surjective, and this implies that this p is projective. So projective objects are such that x1 of them are 0 with respect to anything else. In particular, there are no non-trivial extensions between a projective object of a projective object by any other object, if you're in the category of R modules. So you cannot find a non-trivial extension of a free module, because if you have a ring, any extension like this by anything of a free R module, which is projective, by anything, is going to be trivial. It's a direct sum. And this is already a non-trivial statement to even say. Okay? So if you have any projective guy, you can just replace this by a projective. Then you know, if you have an extension like this of a projective guy by any other guy, then it has to be trivial. It has to be a direct sum. So there are no non-trivial extensions of representations of rings of a projective one. Just this is the statement about P1, X1. We've already proven that isomorphism classes correspond to classes in X1, and X1 is 0. Another trick. So let's suppose that we have, let's take a sequence like this. Let's take an R module, and let's take a projective resolution, P1, P2, P3, and so forth. So this is a projective resolution of A. So what we can do is split this long resolution into a bunch of short exact sequences. So I can look at A. P1 is a bad number to start with. Start with 7. And let's take the kernel of the first map. So now this became this one is surjective because this was a resolution. Let's take the kernel. So that's the short exact sequence. And let's look at the maps. Let's look at homs. Well, the long exact sequence in homology that you get. Okay? So I'm going to look at hom from this into some B, into some other module B. And now this is covariant. This is contravariant. It's hom from this into some B. So what I'm going to get is that I'm going to have some xn of k naught B mapping to x1n plus 1 of AB. Then this comes from xn of P0B, but xn of P0B is 0 because P is projective. If n is bigger or equal than 1. And this maps to xn plus 1 of P0B, but that's, again, 0 because P0 is projective. So I get this isomorphism. Xn plus 1 is isomorphic to xn, and I can just shift the n plus 1 extension of A by B. I can compute by the n extension of K0 with B. So now I continue with this same business, and I look at the map from P1 to P0. So here I have my kernel. Remember how we even constructed this projective resolution. We had the kernel here to P0. And now P1 to P0 factors through this kernel because this sequence was exact. So the image of P1 needs to be equal to the kernel here. So this means that the P1 factors here, and this map is surjective. So let's define the kernel of that map to be K1. And now I look at the long exact sequence here in homology. And I'm going to get that xn minus 1 of P1B maps to xn minus 1. I am stupid. No, it's not so stupid. Xn minus 1 of K0. No, of K1, I'm sorry. Of K1B. It's contravariant. It's covariant. Contravariant. So xn minus 1 to xn minus 1 to xn. To xn of K0B to xn of P1B. So again, if n is bigger or equal than 1, this is 0 because P1 is projective, this is 0 because P1 is projective, and these two guys are isomorphic. So xn minus 1 of K1 is xn of K0, which is xn plus 1 of A. So you can, of course, continue with this way. And we've proven the following lemma. If you have your module A and a projective P0, P1, and so forth, up to, say, Pn, and instead of putting a Pn plus 1 here, you put Kn, which is the Kn here is the kernel to Pn minus 1. Okay, so now this guy is 0. So here Kn is the kernel of Pn to Pn minus 1. So everything here is projective except this guy. This guy might not be projective. Okay? then what we've proven is that x n plus 1 a b, unless I've screwed up the order of these things, but I think this is correct. This is the same thing as x1 kn b. So hopefully I didn't shift by one more than what it should be. So when I took the kernel, yeah, it looks correct, right? So the difference is on k0, which is the kernel to p0, I have a difference of 1. So on k1, I have a difference of 2. On kn, I should have a difference of n plus 1. Did I get it right? Or did I get it for 1 shifted by 1? N plus 1. I got it to be x n minus 1. And then when I get to n, then it's n minus n. No, it's probably, it looks like I have an off by 1 here. And I can't do it on the board. So let's check that this is, it looks like I have an off by 1, right? So in the next step, I'm going to get that xn plus 1 ab is isomorphic to xn minus 2 k2b. So in particular, xn plus 1 ab is going to be xn minus n kn b, which is x0. So I think I want to do this one less, which is what I'm going to need. So let's do an n minus 2, n minus 1, and here's n minus 1. And kn minus 1 is the kernel from n minus 1 to n minus 1. So now this became correct. And here's an n minus 1. Okay. So now I can define dimension. So if you have, so this is only for the category of R modules, or right R modules. This is going to be a different dimension whether or not you're left or right, but it doesn't matter. You can guess. The context is going to be clear. So if you have an R module, then the projective dimension of this R module, A, is going to be the minimum n, if it exists, such that you have a projective resolution of length n. Is a resolution. If there are no finite resolutions of your module, then you would say that the projective dimension is infinite. You might have modules such that there's no finite resolution, projective resolution. Namely, you take any projective, you look at the kernel, you take any projective over the kernel, and that procedure never stops. The flat dimension is the same with flats. With flat modules. And of course, since every projective module is flat, then this dimension is less or equal than that dimension. So this guy here is always less or equal than this. And the injective dimension is the same thing with injectives. So now this is the dimension of a module. Now the global dimension of a ring is given as a supremum of, the global dimension of a ring is the supremum of these projective dimensions of all these modules. The Tor dimension of a ring is the supremum of all the flat dimensions of its modules. And if you take the supremum of all the injective dimensions of a module, you're going to get the same as this. So the global dimension of a ring is, you can compute it by injective resolutions or projective resolutions, and the Tor dimension, which is by definition is less or equal than the global dimension, is given by the supremum of all the possible flat resolutions of all possible modules for a ring. And that's an invariant of the ring. And it's sort of like a striking condition when you first read it, because it sounds like daunting, but if you have a field, for example, then any resolution, any vector field, any module over a field is a vector space, which is free. Therefore, it's projective. Therefore, the global dimension for a field is 0. Anyone is already projective, which is the same as an injective definition, injective dimension, and then it's the same thing as a flat dimension. So fields are objects that have homological dimension or global dimension equal to 0. And it's interesting that this coincides for commutative nice rings with the usual dimension in algebraic geometry. So in algebraic geometry, if your ring is sufficiently nice, and you look at sequences of vectors, so if you have any sheaf over a space, and you ask the question, how many vector bundles do I need to put to cover it? Well, if, say, your sheaf is nice and it's finally generated, then you can always find a resolution by vector bundles of your sheaf. And you can always assure that you're going to have as less or equal than n vector bundles where n is the dimension of your space. So that's a strong statement, which is a topological invariant of a space and is measured by a homological invariant of the ring. So we want to study this. We want to study this homological invariant, and I'm only going to make a quick comment about this because I wanted to use that one of x1. There's something that I'm missing that I want to prove. That is this lemma. Finitely generated. Because flat modules are projective. So we know that every projective is flat. It's not true that every flat is projective, but if a flat is finitely presented, is projective. Actually, even finitely presented. So a module is finitely presented if a module is finitely generated if you have a surjection from a free module that is a finite rank. So that's a finitely generated module. And a module is finitely presented if you have an exact sequence like this. So you have a surjection from a finitely generated module, and the kernel of that surjection is a finitely generated module. So that's a finitely presented module. Now, remember that for any module, we have the Pontryagin dual of that module, which was a homomorphism in abelian groups from A to Q mod Z. So if A is a left module, this is a right arm module. If A is a right arm module, this is a left arm module. So this we defined it to be a dual. This is a Pontryagin dual of a module A. So if A is left module, this is a right arm module, and if A is a right arm module, this is a left arm module. And if we look at A star tensor B, well, we have maps from here to hom AB. That's not what I want. I want to understand the map to hom BA dual. So typically we would look at maps to the dual of this. Remember that we do have the dual, well, the pre-dual of this is this. And the functor that goes from here to the dual was an exact functor. So the functor that sends A to this is exact. Remember, there was exact and it was contravariant. Namely, it sends surjections to injections and vice versa. It sends injections to surjections. So I claim, well, so what is this map? Let's write down this map here first. So you give me here a function. So this is an element, a map from A to Q mod Z. And you give me an element in B. And you're going to extend that by linearity. Any element here is a linear combination of guys like this. And what you want to get is a function. So elements here, what they are? They are, you give me a hom from B to A, and you need to give me an element on Q mod Z. So you give me a homomorphism, phi, from B to A, and you need to give me back an element Q mod Z. Well, so what you can do, you can grab phi, apply it to B, which is your given guy here. That's an element in A. And you have an F that goes from A to Q mod Z. So you can apply it to F. And this is in Q mod Z. So that's a well-defined R module map. I'm sorry, abelian group map. So this, let's say that, let's fix the categories now. Let's say that A is a left R module. So that A star is a right R module. B is a left R module. So this is just an abelian group. This is over R. Let's just take it like this. I want to mix the R there. So let's prove that this is an isomorphism. If B is finitely presented. Shoot. This is not going to take time. This is not going to take much time. I'm going to finish. I want to finish with the proof of that lemma.
This is going to work for any.
This is going to work for, so are you worried about some notariness?
Yeah.
No, I don't think, I might be getting this wrong, but I think it's fine. I don't think it uses any notarian condition on R, this. Let's check it. I might be wrong.
So probably we should ask about notoriety if the model is finitely generated but not presented.
You might be onto something. Let's check. Let's check the proof and let's see if there's. My first intuition would tell me that this does not require R to be Notarian, but you're right that so typically when you have promise of notarianity, then you would start being worried about the difference between being finitely generated and finitely presented. So I'm putting conditions, extra conditions here. So for this might need notarianity, but if I just take it finitely presented, then it does not. But you're right, yeah, thank you. This is actually a good point. I want to take presented here, which is stronger. Oh, it's a weaker statement. Okay, so let's prove this. This certainly does not require. This does not require that the notarianity condition. So if again, you're right. If I ask R to be notarian, then I can change this presented by generated, and then it would work. But let's see. Let's see if B is R to the n. Well, let's see if B is R first. If B is R, then this is trivial. This is the statement that A star tensor with R, which is the same thing as A star, because this is tensor product over R. This is the same thing as hom R A star, but hom RA, a homomorphism from R to A, is the same thing as an element in A. So that's that. So the image of 1 gives me the element in A. So of course this is an isomorphism. Now this is an additive. This is a map of abelian groups. So if it's true for R, then it's true for Rn. So when B is R to the n, this works. And now let's take B to be finitely presented. So let's take it to be Rn and the kernel to be Rm. Yeah. So let's take B to be finitely presented. So let's take an exact sequence like this. Okay, so I've taken this exact sequence. Let's tensor this thing with A star. Yeah, I'm going to tensor this thing with A star. Now, tensoring by is right exact. So this sequence remains exact. Right? I didn't have an R, a 0 here at the bottom. So now, I've just proven that this is isomorphic to Hom Rn A dual. And I've proven that this is isomorphic to Hom Rm A dual. And I have the map here to Hom, there was that map, Hom BA dual, and this to 0. Now, taking duals is exact. This was an exact functor. And Hom is left exact. So that sequence is also exact. That proves that this guy is an isomorphism. So I have these two arrows are exact, and these two guys are isomorphism, then this is an isomorphism. Okay. Yeah, so we didn't need any Noetherian condition, but we didn't need finitely presented. You're right. It's not only for finitely generated. Sorry that I've taken 5 minutes. Let me just finish with the proof of that. Otherwise, we're gonna fail the idea of. Next time, we're gonna have to repeat a lot. Otherwise, so let's just quickly do this. Let's prove that lemma that it's finitely presented. Flat modules are projective, but which is kind of trivial now, because. Remember what it was. Okay. So I'm going to use that. My finitely presented module is going to be this B. And I'm going to use this condition, that Hom from B to somewhere, the dual is just this taking a tensor product, okay, when B is finitely presented. So again, I want to check what it was to be a projective module. So let's say that B is projective whenever I have a surjection A to C. This guy lifts, and remember that this is the same thing as looking at Hom B C, Hom B A, and if you have a map from B to A, then you compose with this by that this is surjective. The other way around. That this is surjective. So I want this to be surjective for every surjection from A to C. That implies that B is projective. Okay, so let's dualize this. Hom B C. Yeah, that's more or less works. To Hom B A dual is injective for every surjection A to C. So I want to, this is injective if and only if, this is surjective if and only if B is projective. But now, since B is finitely generated, finitely presented, then this is the same thing as C star tensor B, and this is the same thing as A star tensor B. And I want this to be injective, so that this is injective. Now B is flat. So this is injective if this is injective. Because flat modules preserve injections when I tensor them by them. And now this is injective if and only if A to C is surjective, which is what I started. So B is projective. So it's hard to come up with flat modules that are not vector bundles. So flat fibrations that are not vector bundles, it's hard to come up with because they cannot be finitely presented. So a good exercise that I haven't thought about is try to come up with a flat guy that is finitely generated, it's not finitely presented, so that you have a surjection like this, but the kernel is not finitely generated, so the underlying ring has to be non-Noetherian, and that is flat and not projective. I think the examples that I gave of flat and non-projective modules were all infinitely generated. I'm not sure.